Welcome back, ladies and gentlemen. We're going to continue with grade 11 chemistry, and as a result, we're going to continue with the grade 10 science review. We're going to be working with ions some more. We've already dealt with binary ionic compounds, polyatomic ionic compounds, and now we're going to be dealing with transition metal ionic compounds that use the stock naming system. You may remember this. It's on page 15 of your booklet. If you guys pull it out, it'll look something vaguely like this. Here it is. Now, what it says here is that some transition metals have more than one possible ion charge. And here's where things get messy. They are referred to as being multivalent. And basically what it comes down to is that you guys may remember in class I asked you how many electrons can you fit on any particular shell. We talked about how the first row, the first period, can fit 2 electrons, and the next 2 can fit 8. And that these 2 down here can fit 16. Now the fact they can fit 16 means that they can put that 16 in an unusual set of arrangements. And because of those differing arrangements, these guys down here have the ability to do weird things. We call them multivalent. Multi meaning many, valent meaning valence, possible configurations in the valence. And for the most part, all of the weirdness is going to be in this area here that we call the transition zone or the transition elements. Now, we're actually going to have a much easier time than they used to have in the old days. In the old days, this was a nightmare because in the old days, we used to name every single transition element with a different name. Yeah. So, for example, iron, good old Fe, which is another one of those Latin ones. So Fe was ferrous. Well, sort of. Half the time, it was ferrous. And the other half the time, it was ferric. Ferrous represented one possible charge configuration, and ferric represented the other one. If I remember properly, I think ferrous is +2, and ferric was +3? Maybe. I might have it in the notes. So this one, ferrous, was +2, and ferric was +3. And this behavior of iron was also seen in other elements, such as Cu for copper, or, as it was called in the old days, cupros and cupric. Notice there's a pattern there? You'd think that means this guy is a 2 and this is a 3, but unfortunately this one is a 1+. I should put it here, and this is a 2+, because copper doesn't get all the way to 3s and 2s. It goes 1s and 2s. But they tried to keep a similar system where they did the OUS ending if it was fairly small valent charges, and the IC ending if it's the bigger valent charges. And the key thing was it was a total nightmare, because instead of having to memorize the good, 118 elements on the periodic table, you had to memorize double that, because every element had multiple flavors. At least 2, sometimes 3, sometimes 4, 5. It's a nightmare, which is why a very smart German chap came along and said, nah, none of that. We're doing this a better way. His name was Stock. If I remember properly, yeah, Alfred Stock, it says right here. And in 1919, yes, it took us until 1919 to figure out that maybe memorizing multiple names per element was a bad idea. Apparently people had not much to do in the old days. They just sat around memorizing elements. Anyway, it says here that the German chemist suggested using a number to indicate the charge of the ion instead of a different name. So instead of ferrous and ferric, why not put the 3 and the 2 right in there? Plus, it's clearer because this and this are different, so why use the same name for the 2 of them? Prior to this, we gave those names based on their charge. Oh, there it is, cupros and cupric. Hey, I think I got it right. Yeah, I did. Awesome. It's always nice when you get things right. Now, since the endings were different, it always caused confusion. So today the stock naming system uses Roman numerals following the metal ion's name to indicate charge. So that first blank is metal. So Roman numerals were used because, broadly speaking, Stock was a German, and the Germans knew Roman numerals because Rome was a big deal in Europe. Now, not everyone knows Roman numerals. So first thing, let me write out the Roman numerals for everybody to make sure that they know what they are. The Roman numerals were based upon the way that the Romans did numbers, hence the name, Roman numerals. And you kind of know them because you do see them every once in a while. Mostly, for example, these days in like movies. These are the first 5. 1, 2, 3, 1 less than 5, 5. 6 becomes 1 more than 5. 7 is 2 more than 5. 8 is 3 more than 5. 9 is 1 less than 10. And 10 is just 10. Why did the Romans do it this way? Well, here's the weird thing about Roman numerals. There's actually only 3 numbers in that entire set. There's just 1, 5, and 10. That's it. So all numbers are made by putting combinations of a few smaller symbols together. So for example, let's see, if I wanted to do 26, I would do 2 10s, a 5, and a 1. And it's up to the other person to know that that's 26. Now, the advantage of this system is that you only need to know a couple symbols in order to do all numbers, which is handy when not everyone has a lot of time to sit around learning all the time. Right? You guys are spending loads of time learning, so if I only have to teach you 3 numbers to be able to do all of them, it makes things pretty straightforward. If I have to teach you, dozens and dozens of different symbols in order for you to understand something, it becomes a lot more difficult. Because think about it. In order to do 26, well, I mean, it's not so bad because it's just 2 6. But at the very least, in order for you to do simple numbers, you would have to learn like 9 other symbols rather than 3. It's only with really big numbers that Roman numerals really fall apart. But they're still useful because, as far as the Europeans were concerned, there were a bunch of numbers that basically everybody knew, but they weren't used very often. Instead, everyone had switched over to what the English usually call Arabic numerals, but actually came from India through Persia. They managed to mess up a lot. They're from India, they got them from the Persians, they decided to blame it on the Arabs instead, I don't know. Anyway, point is, everyone knew these, so they were familiar but not very common. Because there's lots of numbers. I mean, look, right here. We've got 1 pluses and 2 pluses and 3 pluses and 2 pluses. If we started throwing other numbers in there, it might get confusing when we're talking about. Remember when we talked about in the previous day the example of, say, NO3 bracket 2 versus NO32 and how that could be very, very confusing? Well, it's a lot less confusing if instead of using a 2 here, I used a Roman numeral 2. Sort of. Kind of looks like 11. It's not perfect. So, when it comes to the stock naming system, let's give it a try. Let's take it out for a spin. Okay? The example we see here, the very first one, is that we've got iron, bracket, and then we've got 3 in Roman numerals, and then chloride. Okay, so if I write it out with words first so we can work with this. Iron, 3, chloride. Okay, so this is still an ionic bonding situation, so we're still trying to make sure that everything is balanced and everything lines up in every way. Iron is a metal. It goes first. We put Fe. Chloride is a non-metal, so we put it in a second. It's Cl. Chlorine we know because it's in the main group family, we call it. It's one of the binary elements, so it's 1 minus, right? Because if I pull up my periodic table, I see that chlorine is right there, right next to the end of the periodic table, so it's 1 step away. Iron, under normal circumstances, we wouldn't know what it is, but it tells us what it is. It's 3. The Roman numerals here tell you the charge on the iron. This is iron 3 plus. From this point on, this question becomes relatively simple. We've got 3 on this side, 1 on that side. To balance the 2, we need to make sure that I have 3 of those. So if we write the whole thing, we get FeCl3. Done. And this is much easier than, expecting you guys to memorize a bunch of things. Obviously, for example, this one would have been ferric chloride as opposed to ferrous chloride. If I wanted to write ferrous chloride, well, instead of writing ferrous, these days I would write iron 2 chloride. So it makes things less ambiguous, and it means less memorization on your part. All you have to do is remember 3 extra symbols, the Roman numerals, the X, the V, and the I. After that, it all falls into place. 3 extra symbols compared to, what is that, 30 extra names minimum? Yeah, I'll take it. Now, we have another example here. The next one is lead 4 sulfide. Okay, so lead 4 sulfide. Okay, lead is, of course, the metal. It goes first. Lead is Pb. It's another one of those Roman/Latin-based names. Pb stands for plumbum, which is where plumber comes from, because pipes used to be made of lead, because Romans had a lot of lead lying around in Italy at the time, and they didn't really have much else to do with it, so they made pipes and cooking pots out of it. Just one problem. Lead is toxic if you drink anything that comes out of lead pipes or cooking pots. So over a long time, it poisons everybody who uses them. Oops. It's a 4. Now remember, okay, for sulfide, let's put the sulfide down. That's just S. Now remember, the 4 tells you the charge on the lead. The 4 is related to the lead, not to the sulfur. This sulfide has nothing to do with the 4 in any way. The common mistake that students will make is they'll go, okay, lead sulfide 4, boom, 4. This is not true. This is a mistake. It's going to be PbS, and the 4 means this is 4 plus. That's what the 4 means. For the sulfur, you need to look that one up. It's 2 minus. It's right underneath oxygen on the chart. So now that we know this is 2 and this is 4, we can do some crisscross. We bring it down, and we're going to get PbS. We're going to get 2 and 4. This is where people make a mistake again, because you're going to reduce that. You don't need 2 leads and 4 sulfurs. You need 1 lead and 2 sulfurs to make this work. That last step people tend to forget. But that's it. There you go. You're done. That's all you need to do. Realistically, it's not terribly hard, because in the previous one with the binary ionic compounds, we expect that you can memorize the main group elements, the stuff that's in the initial parts of the table, basically everything in the first 2 rows, and you can memorize what their charges are. For both polyatomics and for transition metals, we don't expect that. In the case of polyatomics, we said you can just flip over here to page 3. Boom, right there, you read it off the chart. In the case of transition metals, when you're going from name to formula, they tell you the charge in the name. Very convenient. We haven't done it all yet, though, have we? Because how do I go from formula to name? That's always been the trickier part. Every single time we've done this. Okay, fine. Flip it over to page 16. Let's take a look. Formula to name. What are the steps? Well, okay, it tells us at the top here. It says it's very similar to everything else we've done, except that we have to figure out what the charge on the metal is, because we don't know. Okay, how do we do that? Well, let's take a look at our example. We'll do it in green, I guess. And we'll just erase these to make ourselves some space. Okay? How do we go from formula to name? Because remember, you have to tell the person reading it what the charge is, which means you got to put in the legwork in advance. So the example we've got here is COBr2. So there's our example, COBr2. Okay, step 1. We write out what the names are, and we include as many charges as we already know. Okay, so CO, we'll have to look that one up. That one's cobalt. Cobalt is a transition metal. It's, let's see, where is it? Not exactly sure where this one is. I know it's a transition metal. Wait, is it CO? Yeah, it's CO. I'm not finding it quickly. That's, oh, there it is. It's right next to iron. Oh, silly me. It's right next to iron. It's number 27. So it's definitely a transition metal, which means if it's in the transition metal area, we're going to have to treat it with transition metal naming rules, right? If it's in this area, we're going to have to do something about it. So this is cobalt, and this is bromide. Okay, well, bromide is a main group. That one we know. That one is going to be 1 minus. Okay, no big deal. But now we got to do a little bit of detective work. We know this one is 1 minus, and we know there are 2 of them. Well, if there are 2 of them, and each one is 1 minus, that's going to be like 1 minus times 2 would make 2 minus. And remember, ions are always balanced. So if this side is 2 minus, this side has to be 2 plus. Well, there's only 1 cobalt. This 1 cobalt has to be worth 2 bromides. So this is going to be cobalt, and it's a 2 plus cobalt. So it's going to be cobalt 2 bromide. And there we go. There's how you write it. In this particular case, the 2 here turned into a 2 there. It doesn't always do that, though. All right, let's try another one. We'll use a different color. Let's use blue. Blue's a nice one. So we'll put it right next door, and we'll work our way through the examples. Okay, so it says here, the next one is MnO2. MnO2. Okay, well, Mn, we got to find that one. And that one is the very confusingly named manganese, which is not the same as magnesium. They sound very similar, and it's also right next to iron. It's right before iron, so it's number 25. So manganese, and then oxide. Okay, so that's step 1. Then we write down the charges. Okay, well, we don't know what the manganese is, but we know the oxygen. The oxygen is 2 minus. And we know there are 2 of them. So 2 times 2 means that this whole side of the equation is 4 minus, which means this entire side has to be 4 plus, because these 2 must be the same. So if this is manganese, and it has to be 4 plus, that means this becomes manganese 4 oxide. And we're done. That's it. It's a little bit of detective work, but if you understand about balancing things, it's not hard detective work. It's just, you got to do it. It's a language, guys. Chemistry, everything you learn in grade 10 and everything you're refreshing on now is the language of chemistry. And if it's been a while since you've used that language, it becomes difficult. So, for me, who's had to use this language a lot, it seems very simple, and maybe in some cases I go a little too quickly through it. But you will find that it gets better as you practice it, as you do it over and over again. Just remember, all ions are trying to be balanced. They want a full valence, that's what makes them an ion, and then they want to balance across multiple ions to make a balanced neutral molecule. Ionic compound, technically. So, with that in mind, you guys now have the ability to get started on the work. On page 17 onward, let's see, how many pages is it? 17 all the way up to 19 is practice on ionic compounds. The answers, of course, are located in the teacher notebook. You guys can check them there as you're doing them. Try them first, of course. Don't just copy down whatever's in the notebook. That doesn't really help you learn it. It just helps to make sure that there's enough manuscripts of my amazing notes out there. You guys need to get that information in your brain. And you can't get better at a language by watching other people get better at that language. You need to practice too. So, with that in mind, another fairly short video, thankfully. I will leave it there, and you guys have good luck, and I will talk to you next time.